I guess we can get started. Good afternoon, everyone. I'm Jirong Yi from the Department of Electric and Computer Engineering. My advisors are Professor Wei Yushu and Xiaodong Wu. Thanks for attending my PhD thesis defense, and I'm very glad to have this opportunity to share our work. Today's topic is about the adversary vulnerability of machine learning systems, including theoretical analysis of its fundamental limit and the practical algorithm design. We will first give a brief introduction to machine learning and its robustness issue. Then we will look at the adversary vulnerability from an information theoretical viewpoint and give a theoretical explanation for the adversary vulnerability. After that, we will give information theoretical characterization of the optimality of adversary attacks. In the third part, we will look at the decision regions of machine learning systems on the same task and investigate empirically the possibility of designing an adversary attack, which can manipulate multiple machine learning systems in arbitrary ways simultaneously. We finally conclude the presentation with conclusions and future directions. Machine learning has made great progresses in the past several decades, and many different machine learning models have been developed. These include supervised learning, unsupervised learning, reinforcement learning, ensemble learning, and deep learning. Deep learning is essentially based on artificial neural networks, and it gets its name due to the many layers stacked together in the neural network. For each layer, there can be multiple neurons, and each neuron has a weight vector, W, omega W, and a bias scalar, and a activation function associated with it. And an input image of digit 3 is fed to the deep neural network. Each layer can learn a representation intuitively. As the layer gets deeper, the learned representation will be more efficient and useful for decision making. In the training process, large amount of data will be used to form a loss function, which can guide the search of the weights and biases in all the layers. Once all of them are learned, they can be fixed for making predictions for new input. Deep learning has achieved state-of-the-art performances in many tasks, such as computer vision and natural language processing. However, deep learning systems are also reported to be adversary vulnerable or easily fooled in the sense that very small and carefully designed perturbation in their input can cause them to make ridiculously wrong decisions. The adversary vulnerability makes such systems easy to attack and has raised great concerns about the applications of deep learning in many safety-critical scenarios, such as autonomous driving. Here we give an example to demonstrate the adversary vulnerability. When a natural image is given to the system, it can be correctly classified as pig. However, when adding a small well-crafted perturbation to it can cause it to be misclassified as an ionizer. Adversaries can design different types of adversary perturbations depending on the information revealed to them and their attacking goals. In the most beneficiary case for adversaries, all the information is known to them, such as system architecture, configurations, training algorithms, and the data distribution and generation. In the most disadvantageous situation, the adversaries can only have a set of data samples, which themselves may not be trusted. There can be different goals for the adversaries. Two most common attacking goals are misclassification and targeted misclassification. In the former, the goal is to fool the system to make a mistake, and it is also called untargeted attack. The latter requires the adversary to fool the system to make a specific mistake and is also called a targeted attack. Formally, uh, these two attacks can be formulated as follows. In targeted attack, we want to find a small perturbation data for an input X such that a well-trained system, F theta star, will classify it as any neighbor but not its true neighbor Y. In the targeted attack class, the goal is to find a small perturbation which can force the system into classifying the modified sample as particular wrong class Y prime. Here, theta star contains all the learned parameters of the systems. Despite large amount of effort devoted to the adversary robustness of deep learning system, there are still many challenges and open problems. First of all, the working mechanism of deep learning is not clear even until now. And deep learning system usually works as a black box. Secondly, a well-accepted theoretical explanation of adversary vulnerability has not been established yet. For example, the deep learning systems can recognize there is a face in a face image, but it does not tell us how it arrives at such a decision. Besides, when a well-designed small perturbation is added to the face image, the system can recognize it as a bird. Still, we don't know why it makes such a mistake. Another challenge is the establishment of a performance guarantee for defending algorithms and optimality of adversary attacks. In the past several years, the community witnessed the um, continuous competition between the attackers and defenders. Whenever a defending or attacking algorithm is claimed to be the strongest, it will soon be bypassed by stronger, more advanced attacking and defending approaches. Last but not least, the decision regions of machine learning systems are also considered to be an important aspect of them, but the decision regions of deep learning systems are not fully investigated yet due to the high non-convexity and non-smoothness in high-dimensional space. For example, a three-class classification task in 2D space, the KNN and random forest, the naive Bayes, and the classified ensemble can have different decision regions for the same task. Now let's look at the theoretical explanation of adversary vulnerability. There are several lines of works towarding the theoretical understanding of adversary vulnerability of deep learning systems. The system lines, the first line starts from a quasi-linearity assumption in the data sample space. The second line uses the curvature of the decision boundary of the learning systems to characterize the adversary vulnerability. Another line looks into the closeness or distance of the decision boundary to data submanifold in different classes. However, none of them are both are theoretical and empirically easy to verify. We propose a new framework for understanding of the adversary vulnerability um, of the vulnerability phenomena, which is both theoretically rigorous and easy to verify empirically. There are also other works about designing different designing algorithms such as adversary training, denoising, and reconstruction method. For example, in reconstruction defending method, we use a learned representation to reconstruct an approximate of the nature image, and deep learning system will make decisions based on the approximation. However, none of these methods has theoretical performance guarantees associated with them. We propose a class of defense algorithm, which is a generalization of the reconstruction method and has theoretical guarantees with it. Our starting point is an analogy between communication model and classification model. In communication, a source message U first goes through an encoder to get a code word X, and the code word will be transmitted via a communication channel. The receiver will decode the received code word to estimate the source message as U height. This is highly similar to what happens in classification. In classification, nature sample X is synthesized from a given neighbor U, and it can be corrupted by perturbations before it is fed to the classifier for prediction of its neighbor U height. We can zoom in the classification component. In communication, to verify the validity of the decoded message, the receiver can let the estimated message go through the same encoding process to get an estimate of the received code word. If the estimated code word differs greatly from the received one, the receiver can claim that the estimated message is not correct. The idea can also be applied to detect adversary attacks in classification. The difference is that we assume there exists a compression process before the classifier gives the predicted label. We will show later that the feature compression accounts for the adversary vulnerability, and a defense method inspired by feature compression can guarantee the detection of adversary attacks. The feature compression assumption is motivated by several observations. In the example of 10-class classification for handwritten digits, the input is an image of size 28 by 28 or a vector of 784 dimensions. The deep learning system finally returns 10-dimensional probability vector, and each element is the probability for the sample to be within the corresponding class. The class which has the highest probability will be predicted label for the given sample. As we can see, there is a huge reduction from 784 dimensional space to a 10-dimensional subspace. We now give an example to illustrate the connection between the feature compression and adversary vulnerability. Suppose we have two data manifolds in 2D space which contain data samples from different classes, and the distance between them is d height. When both of them are projected onto a 1D space or a line, the distance between them is in 1D is just d low, which is dramatically smaller than d high. In this case, if we perturb a sample in class B slightly in the 2D space, the sample can jump to class A in 1D space or the decision space. The classifier can be fooled within this situation. We can give theoretical explanation for the adversary vulnerability using feature compression. This connection between adversary vulnerability and the feature compression also motivates us to propose a defending method. Let's first look at the case with linear compression function. We assume the linear compression is achieved by a fat Gaussian matrix A in R m by n. And we assume the sample Y fed to the classifier contains perturbation W, which can be either arbitrary or random. For simplicity of presentation, we also assume the true class label of sample X to be 1. We also define the concept of epsilon L robustness of a classifier G for given sample X. If the probability for the classifier to give the correct label of natural sample X to the probed sample X plus W is greater than 1 minus epsilon, then we say the classifier is epsilon L robust for sample X. With the above setup, we have the following claims. When it's a high probability over the random matrix A, an adversary can design a perturbation W with small magnitude such that it can fool the classifier to classify the perturbed sample as a specified wrong class. This essentially characterizes the adversary vulnerability to targeted attacks. And we can also characterize the phenomena in untargeted attacks. With high probability over the random matrix A, an adversary can design a small perturbation W such that the perturbed sample will not be classified as the correct label 1. Here I is a constant and Ci is the code word in class I, which is closest to X. As we can see here, the upper bound of the perturbation magnitude depends on the compression ratio m to n. For example, in targeted attacks, the m over n becomes small. When the m over n becomes smaller, the upper bound of the perturbation magnitude will become smaller, which means it will be easier to perform attacks. In untargeted attack case, when m over n decreases, the upper bound also goes up, which means the untargeted attack is more difficult to achieve. I'm sorry. This is because when m over n goes down, there will be less number of classes. In the extreme case, there are only 2 classes, and the untargeted attack becomes targeted attack. those attacking becomes more difficult. I'm sorry, yeah. We can also show that defining method based on feature compression. We can also show that we can also characterize the robustness of the deep learning system to random perturbation. Assume the perturbation is randomly sampled from a unit sphere, then with high probability over A and W. The targeted attack with random perturbation will not be possible if the perturbation magnitude is not big enough. We can also claim that the targeted attack with random perturbation will not be possible if the magnitude is not big enough. We can also show that the defending method based on the feature compression can be guaranteed to detect adversary attacks. More specifically, we assume W is a random, is a successful targeted adversary perturbation and can force the system to give the wrong label I. Then our approach can detect adversary attacks even if the perturbation magnitude is small. I'm sorry, yeah. Uh, we can also give characterization of adversary vulnerability of classifiers with nonlinear compression functions. For an epsilon greater than 0, we define alpha epsilon as the variation in the output of the compression function h caused by the adversary perturbation, and beta O epsilon as the variation caused by the random perturbation of the same magnitude from a sphere. Then we can show that the ratio of the alpha epsilon to beta epsilon 0 is lower bounded by square root of n over m. This means that the adversary perturbation can always achieve larger variation than the random perturbation can. Thus, the system will always be more vulnerable to adversary perturbations. We now give empirical results to demonstrate the performance of our approach. In this example, when a nature image from class 9 is fed to the system, we can get its estimate as in A. And we can see that the difference between the nature sample and its corresponding estimate is very small. It's very small. When we feed an adversary sample, which is actually from class 2 but misclassified as in class 9, we can get an estimate as in B, and the difference is very big. We also demonstrate the statistical performance. A set of nature samples are fed to the system, and we get the estimate for each of them, and then calculate the difference between the nature samples and their estimates. As we can, we then plot the histogram of the difference, and we also do the same thing for a set of nature, for a set of adversary samples, as we can see from the figure. The mean square error for the nature samples is concentrated around 0.05, while that for adversary samples is concentrated around 1. And this huge gap between 0.05 and 1 allows us to select the threshold for detecting adversary samples. We now demonstrate the quantitative result of the proposed approach. For each of the classes from 0 to 9, we use our approach to distinguish a set of nature and adversary samples. Though Ben C is the ratio of the number of identified nature samples to the total number of nature samples. Though subscript alarm is the ratio of the number of unidentified nature samples to the total number of nature samples. Though subscript superscript C is the ratio of the number of identified adversary samples to the total number of adversary samples. Though subscript missing is the ratio of the number of unidentified adversary samples to the total number of adversary samples. As we can see, our approach can achieve very small missing rate and false alarm rate for all the classes. We now summarize this section. In this section, we give an explanation of the fragility of deep learning systems using the feature compression assumption. And our explanation is applicable in classifiers with compression component. We also proposed the trusted but verified approach for detecting adversary samples. And our empirical result on real data set demonstrate the effectiveness of approach. Part of this work is published in IEEE International Symposium on Information Theory 2019. We now look at the information theoretic optimality of adversary attacks. This is motivated by several observations. In the past several years, many empiric defending or attacking algorithms are claimed to be the strongest, but they are soon surpassed by more advanced approaches. Besides, the theoretical optimality of adversary attacks is never touched before. In 2017, Zip and Tishby showed that mutual information can be used to characterize the properties of deep learning systems. In previous section, we showed that the feature compression can be characterized by dimension nanity reduction. In this section, we will use mutual information to characterize the feature compression concept. Our goal is to provide a theoretical framework for characterizing the optimality of adversary attacks. We model the classification task as follows. We generate a nature sample X according to a label U, and the classification simply estimates the U from X. In adversary situations, the X can be corrupted by adversary perturbation E. The tool we use is a generalization of rate distortion theory. In rate distortion theory, the goal is to obtain a representation Y with finite precision for X in real number set, so that the estimated or the decoded X will not be too far from the true X. In classification, the X is generated according to a label, and the goal is to estimate the label rather than X. Under the above framework, if we assume a random variable U in calligraph U, with calligraph U being a finite set of all class neighbors, then the error probability will be lower bounded by a monotonically decreasing function of the mutual information between U and X. This implies that minimizing mutual information IUX can result in larger classification error, and we can perform adversary attacks by minimizing mutual information. More specifically, we formulate the problem as in 6. We want to find a conditional distribution for perturbation E such that after it is added to the nature sample X, the mutual information will be minimized. We want to point out that our attacking method is independent of system configurations, the attacking method and defending method. Thus, it gives the fundamental limit of adversary attacks. Here, we give the conceptual framework of our proposed attacking method. The natural sample is generated according to a label U and is corrupted by adversary perturbation, which is characterized by the random variable E with bounded energy. This U is carefully designed so that the mutual information between U and X plus E can be minimized. We now consider the case where the neighbor follows a Gaussian distribution with zero mean and variance A squared. We assume the noise W follows a zero mean Gaussian distribution with variance sigma squared. We also assume the perturbation E to have a bounded energy D. Under the above setup, the optimal perturbation E must have zero mean and is jointly Gaussian distributed according with W and U with covariance matrix F as specified in equation 7 here. Here, the X and Y is the solution to an optimization problem defined in equation 8. The corresponding minimum mutual information in this case is given as follows. It's basically the 1/2 minus 1/2 of 1 minus this specific term. As we can see, if D goes up, the mutual information will decrease. those adversary tag can be achieved. We now consider the case where multiple Gaussian copies with a linear projection is used. We assume we have a group of Gaussian random variables u1 up to un, which are RID according to zero mean Gaussian distribution with variance sigma square. We assume that sample X is generated via a linear transformation of the neighbor vector U, which is achieved by multiplication with a matrix H. Assume the matrix H to have a signal value decomposition as QC V transpose, while C is a K by K diagonal matrix with singular values on its diagonal. We want to find a perturbation E for X so that the mutual information can be minimized. And we assume the upper bound of the energy, perturbation energy is bounded by the sum of the squared signal values of H. Uh, I'm sorry, yeah. Under the above setup, we have the following. There is a positive number tau, which acts as a threshold for controlling the energy assigned to each of the signal vector direction of the linear projection matrix H, so that the sum of energy along each signal vector direction is equal to D. The smallest mutual information in this case is the sum of mutual information achieved along each direction. Basically, it's it's the this system log sigma I squared divided by di, and then take half of it. The perturbation which can achieve this mutual information is given by the product uh, between Q and lambda. Here, Q is the left signal signal vector matrix of H, and lambda is a Gaussian random vector with RID element. Um, and when the adversary can design a perturbation with energy greater than D, with energy greater than the sum of the squared signal values, and optimal uh, adversary attack will be E star equal to the negative of H times U. And corresponding the minimum mutual information in this case will be just 0. We now consider the case of attacking binary classifier. We assume the U and H, U and X follow a joint distribution characterized by A, B, C, D. And the distribution of the perturbation conditioning on U and X is characterized by P1, P2 up to P4. Then the original mutual information minimization problem can be simplified as in equation 9. And we want to find P1, P2 up to P4 from the interval 0 and 1 to minimize the mutual information under a linear equated constant of them. Under this setup, we can characterize the optimal P1, P2 up to P4 as follows. There must be a non-negative lambda star such that the equations in 10 and equations in 11 must be satisfied, must hold. Moreover, if now the ABCD is 0, then we can claim the optimal perturbation E must achieve a distribution of Y which is independent of the label U. Thus, the optimal attack can achieve 0 mutual information in this case. We now give empirical result to demonstrate our ideas. In this first set of experiment, we plot the ratio between error probability error lower bound and the mutual information. As we can see, the error probability lower bound increases as we reduce the mutual information. For example, in the case with 10 different classes, the mutual information is 0 when the mutual information is zero, it shows that the error probability lower bound will be greater than zero point 0.6, will be greater than zero point 0.6. This is intuitive. When the mutual information is zero, we simply make a random guess. Then the probability for making mistakes is just point 0.9 if we assume uniform distribution for the labels. In the second set of experiments, we show how the mutual information is affected by the perturbation energy budget in the case with single Gaussian random variable. As we can see, when the energy budget increases, the mutual information will decrease. In the third set of experiments, um, we show how the mutual information is affected by the number of copies n. A larger ratio n over m indicates more copies. As we can see, when we increase the ratio, the mutual information also increases. In the first set of experiments, we show how the mutual information is affected by the energy budget in the binary classification case. As we can see, the mutual information decreases when we reduce the energy budget of the perturbation. We now summarize this section. We show that the mutual information between perturbed sample and the label is highly related to the classification error lower bound, and an adversary can achieve attacks by minimizing the mutual information. We give theoretical characterization of the optimality of adversary attack, and it is independent of the system configuration and the training algorithms. It implies that adversary vulnerability is unavoidable and that the transferability of adversary sample is inherent. We now look at the selective adversary attacks, which is highly related to the transferability of adversary samples. The selective adversary attacks are motivated by several observations. First of all, we shown in the last section that the transferability of adversary samples is inherent, and many empirical results also demonstrate this. However, it is reported that only the adversary samples are transferable, while the adversary neighbors are not. This means even though an adversary sample, which can form one particular class, can also can for one particular system can also for other systems, but it cannot force them into making the same wrong decisions. Secondly, there is an increasing volume of work on the transferability by looking at the decision regions of different machine learning systems over the same task, but very limited attention is given to how the decision regions of different systems over the same tasks differs. We propose a selective adversary attack framework and provide empirical evidence for demonstrating the difference between different classifiers. The, the conceptual framework is like this. We are given a group of classifiers F1 up to Fn, and we want to find a small, okay, all these classifiers are well trained, and we want to find a perturbation data for X, so that the classifiers will classify the modified sample as U1, U2 up to UN. And we assume that the true label for X is U0, and the labels U1 up to N may or may not be U0, and they may or may not be the same. We can formulate the attacking model as follows. We want to find the small perturbation so that the first N classifiers will be forwarded into making wrong decisions, while the rest N minus N classifiers will continue to give the correct predictions. We now give empirical result to demonstrate the ideas. We use totally 4 classifiers. In the first case, we want to find a perturbation which can for the first classifier, but not the rest 3. In the second case, we want to for the first 3 classifiers into making different labels, but now the last one. As we can see that the perturbation we can find in the first case has a larger magnitude than that in the second case. This is quite intuitive since more diverse the label predictions actually imply more constraint in the design of attacks, and attacks will be more difficult to achieve as indicated by a larger magnitude. We now summarize this section. Uh, we showed we showed that neighbors of multiple classifiers can be manipulated arbitrarily uh, and simultaneously. And this actually implies that the decision regions of different classifiers on the same task can differ greatly from each other. Now let's conclude this presentation and point out several future directions. Here are the conclusions we can make from the previous presentation. First of all, feature compression can actually account for the auditory vulnerability of machine learning systems. We can either characterize this property by dimensionality reduction or the mutual information loss. Secondly, uh, the definitive method inspired by the feature decompression can actually be guaranteed to detect the auditory samples with high successful rate. The third point is auditory tags can be actually achieved by minimizing the mutual information. And from the perspective of information theory, we can characterize the optimality of auditory attacks. The last point is auditory vulnerability of machine learning systems is unavoidable, and the transferability of these auditory samples can be inherent, and the decision regions of multiple systems on the same task can be uh, can be greatly different. Here are some future directions we can explore. First of all, uh, it is it is interesting to design defending algorithms inspired by mutual information maximization. And second one is the design of practical attacking algorithms by minimizing mutual information. Another very interesting topic will be the theoretical characterization of decision regions of machine learning systems and transferability of auditory samples. The last point will be how to scale up the attacking and defending algorithm inspired by mutual information uh, in real-world application, because calculating the mutual information in practice can be always challenging. The content in this presentation appeared in the following publications. Here are other topics that are included in the thesis but are not presented here. Um, and this includes the following. The first one is about the necessary and sufficient condition for no rank matrix recovery. And the second one is about the uh, robustness of virus detection. And the third one is about alternate detection with the help of deep learning. That's the first one is about the separation-free super resolution in statistical signal processing. Okay, in spectrally sparse signal recovery, uh, we formulate the problem as follows. We want to recover signal X and its underlying frequencies Fk from compressed time domain observations B. And here this signal X is consisting of a group of exponential signals here. And our contribution for this work is that in previous work, the success of the proposed approach requires the separation among the underlying frequencies F1 up to Fr. However, such a frequency separation is not required by our approach. In the second work, we investigate the necessary and sufficient conditions for no rank matrix recovery. And the problem is formulated as follows. We want to recover a low rank matrix X and its undersampled from its undersampled measurement. Basically, it's a minimization of the nuclear norm of a low rank matrix subject to the measurement constraint. And our contribution here is that we show that the previous necessary and sufficient condition established by OMAC, etc., by OMAC is not correct, and we instead give a correct necessary sufficient condition for recovering low rank matrix Y from solving this optimization problem. And this work is published at IEEE Transactions of Information Theory. I'm sorry, this is not correct. Yeah, it's transaction of information theory. Another work I want to introduce is the alternate detection using generative model. And the problem is like this: we want to recover a signal from its compressed measurement, which are corrupted by outliers E. Here this M is a measurement matrix. And our contribution here is that the sparsity assumption of the ground truth signal X is required for previous works to work, for previous approaches to work. However, our method does not require the sparsity of X. Instead, we use a deep neural network to learn useful structural information about X so that the signal can be recovered. And this work is published as Signal Processing with Adaptive Sparse Structured Representation Workshop in 2019. And another piece of work I want to briefly talk about here is about the robustness of virus detection. I'm sorry, it's not outlier detection. No, it's not this. It's virus detection. Okay, the problem is how we can identify individuals infected with virus and estimate the virus amount from poor testing with potential corruption. For example, the problem can be formulated as this way. We want to recover this X from Y. And our contribution here is the empirical demonstration that higher testing accuracy, higher testing capacity, and increased test reliability can be achieved in virus testing simultaneously. Here is a list of other topics that I worked on but are not presented. Yeah, I think that's all for this presentation. Thank you for your time.